Assalamualaikum and hi. My name is Ahmad bin Azhar and today I will present about my research proposal titled Air Quality Monitoring Before and During Process Conversion of Sugarcane Bagasse into Activated Carbon via Pyrolysis assisted by zinc chloride activation. Let us begin with the background and research problem. University researchers often spend upward of 90% of their time inside laboratory environment. Literature shows that poor indoor air quality can lead to significant health conditions, including respiratory illness, headache, fatigue, and even sick-burden syndrome. While extensive material science literature focuses heavily on optimizing the chemical activation of sugarcane bagasse, the immediate safety risks to the researcher conducting this experiment are heavily overlooked. The study is highly significant because it addresses the specific safety gap. By quantifying the unseen chemical risks such as invisible carbon monoxide, carbon dioxide, and fine particulate matter, we can provide empirical data to evaluate and upgrade our local exhaust ventilation system, and ultimately this ensures the strict compliance with Malaysian Department of Occupational Safety and Health guidelines. Next, we move to the objective and research question. To guide this study, I have established three main objectives alongside corresponding research questions. My first objective is to monitor the baseline indoor air quality level before any chemical activation begins. This answers our first research question regarding the raw ambient condition of the laboratory workspace. Secondly, I intend to monitor this exact same parameter, namely PM2.5, PM10, carbon dioxide, carbon monoxide, relative humidity, temperature, and air velocity during the chemical impregnation process using zinc chloride. This addresses our second research question, which is quantifying exactly how much this hazardous parameter increase during active chemical handling. Finally, my third objective is to evaluate laboratory safety by benchmark our recorded real-world data directly against the Malaysian DOSH Industrial Code of Practice 2010 standards. This answers our final research question, which is whether our laboratory environment comply or not with the local safety threshold. Moving on to the methodology. The study adopts a laboratory-based experimental design utilizing a quantitative approach to analyze atmospheric variation before and during chemical processing. We will rely on two high-precision instruments for data collection. First, the EVM environmental monitor will be deployed to continuously track particulate matter, specifically PM10 and PM2.5, as well as toxic gas concentration of carbon monoxide and carbon dioxide. Second, a universal IAQ instrument, the TESTO 400. It will capture microclimate parameters, namely temperature, relative humidity, and air velocity. The data collection is cleanly split into two main phases, monitoring the undistributed baseline environment, followed by tracking real-time fluctuating during the chemical impregnation process. Please note that the subsequent pyrolysis process is exempted from the specific indoor evaluation because it takes place in an outdoor laboratory setup. What do we expect to achieve from this study? We anticipate delivering a comprehensive baseline air quality profile, real-time process mapping of chemical emission, strict national compliance verification, and actionable standard operating procedure for university PPE and ventilation use. More broadly, this research directly fills a persistent academic gap by providing rare empirical industrial hygiene data within a material science context. It creates a brand new chemical baseline dataset for zinc chloride processing. successfully bridged material science with industrial hygiene engineering, and crucially, it served as a clear, replicable safety testing model that other universities can use to protect their student researchers.